Now the next mode of heat transfer is radiation. Radiation heat transfer occurs due to the electromagnetic waves. Now the thing is, what bodies emit electromagnetic waves, or what bodies take part in radiation heat transfer? You might know that over here we are more concerned in those radiation which we may call thermal radiation, means due to temperature, and all the bodies which are above 0 Kelvin, which are above absolute zero, all the bodies which are above absolute zero emit thermal radiation. Means any body whose temperature is above 0 Kelvin. So all the bodies that we see around us have temperature above 0 Kelvin, like the tables, chairs, sun, walls, ground, etc. So all those bodies are the bodies that are at a temperature above 0 Kelvin. So all these bodies in fact emit thermal radiation, and that radiation is in the form of electromagnetic waves. And a peculiar property of electromagnetic waves is that they do not require any medium to travel. Thus, unlike conduction and convection, the radiation heat transfer does not require the presence of an intervening medium, because the electromagnetic waves do not require any medium to travel. They can even pass through vacuum. So if we, for example, if say there is heat transfer taking place between a system to its surrounding, and say that is a heat loss. Heat is being lost from a system to its surrounding, and we want to reduce that heat loss. So what can be done at most is that we can make the conduction and convection losses to approximately zero. However, we cannot make the radiation losses zero. How we can do that? If, for example, there is a pipe through which the heat is being lost to the surrounding air, if we put that pipe in a vacuum, in a sleeve, and make the annulus vacuum, so through the vacuum, conduction and convection losses would be minimized to almost zero, but radiation heat loss will still be taking place, because the electromagnetic waves do not require any medium to travel. So as I just said, that in heat transfer we are interested in thermal radiation, and the thermal radiation is emitted by the bodies due to their temperature, owing to the temperature, because any body whose temperature would be above 0 Kelvin would be emitting thermal radiation. Now you would have come across this expression which says EV is sigma T4. First of all, this is not the expression for radiation heat transfer, because in here this E refers to emissive power, and not the heat transfer. What is emissive power? Emissive power is in fact a measure of the amount of radiation that would be emitted by a body, and that emissive power is directly proportional to the temperature. So the higher the temperature of the body, more would be the radiations emitted out of it. So the point over here is that the radiations emitted would be a function of the temperature, and the radiations would be emitted by a body by virtue of temperature. Radiations would be emitted by a body by virtue of temperature. So we call it emissive power. So E refers to the emissive power, whereas B in the suffix refers to the black body. So the emissive power of a black body is directly proportional to absolute temperature raised to the power 4, and the constant is sigma, where sigma is called the Stefan-Boltzmann constant, the value of which is 5.67 exponent minus 8 with those units, watts per meter square, Kelvin pole. Now EB sigma T4 is in fact the emissive power, means it tells us how much radiation would be emitted out of a body, emitted out of a surface, if that body or if that surface is at a particular temperature. In fact, radiation is a volumetric phenomenon, but we consider it as a surface phenomena as well, because the radiation would be emitted by the body. The radiations that would be emitted by the body would leave the surface of the body, or would come out of the body when it would leave the surface. So we can also call it a surface phenomena. So, so EB is the emissive power of a black body. And what is a black body? A black body by definition is a perfect absorber and a perfect emitter. It is by definition a perfect absorber and a perfect emitter. What is meant by perfect absorber? Perfect absorber means that it will absorb all the radiation that would be incident upon it. That would be incident upon it. So if we have a black body placed in a room, for example, so the room would be at a temperature, the walls of the room would be at a temperature above 0 Kelvin, and they would also be emitting certain radiation. So those radiations, some of those radiations would be incident, would fall upon that black body, and if that body absorbs all those incident radiation, then that body would behave as a black body. Or if that body is a black body, then it will absorb all the radiation that would be incident upon it. This is what is meant by perfect absorber. The second thing is perfect emitter. Perfect emitter means that that no body can emit more radiations than a black body at a particular temperature. No other body, what we call a real body or a grey surface, can emit more radiations than a black body at a particular temperature. Means a black body would always emit more radiation. A black body would always emit more radiation than any other real surface or a grey surface. If both the surfaces, if the black body and the other real surface are at the same temperature. This is what is meant by perfect emitter. And you would certainly have seen this expression where E is epsilon times sigma T4. Over here we do not have B in the suffix. Over here we do not have a B in the suffix. It means that this is not the emissive power of a black body, rather this is the emissive power for a real surface or a grey surface. And you can see the similarity between these two expressions. They are almost the same. We have a sigma T4 in here and we have a sigma T4 in here as well. The only thing is that over here it is being multiplied with a sigma, with an epsilon, where epsilon is the emissivity. So we can write that E is epsilon times EB, and emissivity would range between 0 and 1. So emissivity would range between 0 and 1. So therefore E would always be less than EB. E would always be less than EB, means the radiations that would be emitted by a real surface would always be less than the radiation emitted by a black body if both are at the same temperature. Of course, if you increase the temperature of a real surface, then it may emit more radiations than a black body. So therefore, in order to compare the two, we need to have the temperatures of the two bodies the same. And epsilon would be 1 for a black body. The value of emissivity would be 1 for a black body. So over here you can see the radiation heat transfer. If this is a fire, the heat, and out of this fire the heat is coming out, the energy is coming out. So it will then reach the hands via radiation due to the electromagnetic waves, due to the thermal radiation. The sun is also a body at a temperature above 0 Kelvin. In fact, the average temperature of the outer surface of the sun is supposed to be around 5800 Kelvin. We will discuss that in detail in chapters 12 and 13 when we would be discussing radiation in detail. The sun being a body above 0 Kelvin is also emitting radiations. And we have got the space in between. We have got a large vacuum in between the sun and the earth. So the radiation would pass through that space because they do not require any medium to travel. They would pass this vacuum. The solar radiations would pass this vacuum as they do not require any medium to travel, and then they will reach the earth. Now that expression that we were looking at a while ago, PV was sigma T4, was regarding the emissive power. When we come on to the heat transfer due to radiation, the expression that is given is at the basic level is given as sigma epsilon A T14 minus T surrounding 4, where this expression is not a very general expression. Rather, in fact, it is a very basic expression, and it has got certain limitations. What are those conditions, or what are those constraints, or what are those limitations? This expression is valid for a body which is at a temperature Ts, having an area of As. So you may write this area as A or As. As or A means the area of the surface, and epsilon is the emissivity of the surface. So we have got this surface. The temperature of which may be taken as Ts, or it may be taken as T1. It is the same thing. And this surface is placed in surroundings. And the surrounding is at T surrounding. So one body is at T1 or Ts, and the other body is T surrounding. Other surface is T surrounding. So these are the two temperatures of the two surfaces between which radiation heat transfer is taking place, and A is the area of this surface, and epsilon is again the emissivity of this surface, and sigma as usual is the Stephen-Boltzmann constant, the value of which is 5.67 exponent minus 8. This equation can only be used if we place a body in surroundings. This expression cannot be used between any two bodies. And for example, if there are two walls, if we are sitting in a room and if there are two walls, let's say the roof and the floor, right? The roof and the floor. There are, if it is a rectangular or a square room, there would be 6 walls, 4 vertical and 1 ground and 1 on the top, the floor and the roof. So if we want to find out the heat transfer due to radiation between the top roof and the bottom floor, and then we cannot use sigma epsilon A T14 minus T surrounding 4. Rather, we have a certain modified equation or an advanced equation that will be used to find out the radiation heat transfer between the two bodies. The reason is that right now we are only considering epsilon. Right now we are only considering epsilon, the emissivity, and this is the emissivity of this surface, which is at a temperature of Ts or T1. When we are having the top floor and the bottom, the top roof and the bottom floor, and then there would be an emissivity of the roof, and then there would be an emissivity of the floor. So the thing is that whether we should be referring to epsilon 1 or epsilon 2. Would we be referring to the epsilon of the emissivity of the roof or the epsilon of the floor? So both will come in play, but we will learn how do we write those equations later when we will reach chapter number 13. In fact, chapter number 12 of our book refers to the or deals with the radiation physics, whereas 13 in fact deals with the radiation heat transfer. So we would be learning about some physics of radiation in chapter 12. However, the heat transfer due to radiation means the expression of Q will be dealt with in chapter 13. So right now, this epsilon is the epsilon of this surface. And this surface is placed in large surroundings. So now there are several questions that could arise. For example, let me give you an example over here. Let's say if this is the surface, the top surface, and this is the bottom surface, right? This is the floor, and this is the roof. This is the roof. So the roof will emit radiations which will fall on the floor, but it will also emit some radiation that will not fall on floor. Similarly, floor will emit radiation that will fall on roof, and the floor will emit radiation that will not fall on the roof, rather it will be incident upon the side walls. So we in chapters 12 and 13 we will also be taking that fraction into account, which is called the view factor or the shear factor. Right now, what is happening is that since this body is placed in a large surrounding, so all the radiations that are leaving the surface are in fact going to the surrounding. So that fraction is in fact 100%. All the radiations that are leaving this surface are in fact, where are they going? They are in fact going to the surrounding, and they are going nowhere else. So that fraction which is leaving 1 and is being incident upon 2 is being incident upon the surroundings is in fact 1 or 100%, and that is why that is not visible in this expression. It is not visible in this expression. Similarly, where is the epsilon of surrounding? In fact, epsilon of large surroundings is taken as 1. Why? It means that large surroundings or large enclosures or large furnaces or large rooms are considered to be black bodies, and that is why their epsilon is taken as 1. Let me explain you why do we take the emissivity of large surroundings as 1. Now consider it is a large room or a large enclosure, and say that a radiation comes in. Right? So when the radiation would come in, it will hit the surface of this large enclosure. Now what will happen is that a part of this radiation will get absorbed within the surface, and a part of it will get reflected. Right? So because and a part of it will get reflected. Say the magnitude of this radiation is suppose 5, just for the sake of understanding, and 3 gets absorbed, and then 2 gets reflected. So upon the second hit, when it would get reflected, it will hit the surface again, and upon the second hit, what will happen is that some part of this will get absorbed and some part of it will get reflected. So say out of that 2, 1 gets absorbed and 1 gets reflected. Now when the reflected one will again hit the inside surface of that large enclosure, so then it will get absorbed. So what is happening is that a radiation which is coming into the large enclosure will ultimately get absorbed within the enclosure after multiple interactions, after multiple hits. So this large surrounding or large enclosure or large room will in fact act as a perfect absorber, or almost a perfect absorber, and in that sense they resemble to a black body being perfect absorbers, and therefore the emissivity of the large surroundings or large enclosures or large rooms or large furnaces are considered to be 1. The emissivity of those surfaces are considered to be 1, and therefore for the very same reason that epsilon of surrounding is not being shown over here, because that is 1. So this epsilon is the epsilon of this surface. So those are those things, those are those advanced things that we would be looking at when we would be discussing radiation in detail. Now if we start with Q is with the same expression, Q is sigma epsilon A T1 4 minus T2 4 or T surrounding 4. Now over here it is A to the power 4 minus B to the power 4. So if we do the factors, it would be A square minus B square times A square plus B square. So it would be A square plus B square times A square minus B square. And then this is A square minus B square. And if we do the factors, so the factorization will yield A minus B times A plus B. So sigma epsilon A remains the same. This T1 square plus T surrounding square remains the same. This A square minus B square has been written as A minus B and then A plus B. So what I do now is that if I bring area in here, I am not doing anything. I am only bringing this area. With this delta t, right? T1 minus T surrounding is delta t. This was not delta t, it was T1 4 minus T surrounding 4, but now this has become delta t. And if we now compare it with the expression for convection, which was HA delta t, so we can see that there is an A and then there is a delta t. So whatever is left is in fact something similar to the convection coefficient, similar to H, and this is what we call HR. Where HR refers to the radiative heat transfer coefficient. You can see that this thing has been written as HR. A remains A and T1 minus T surrounding remains T1 minus T surrounding. So this HR is in fact the radiative heat transfer coefficient. So therefore we may write the expression for convective heat transfer coefficient as HA delta T, or in some texts they write it as HC A delta T, where they put C in the suffix of H to call it convective heat transfer coefficient. And similarly we can write the expression for radiation heat transfer as HRA delta T. So HA delta T for convection and HRA delta T for radiation, where again R would be written in the suffix of H, and that would refer to the radiative heat transfer coefficient. You do not need to remember this expression for HR. HR is in fact sigma epsilon T1 square plus T surrounding square times T1 plus T surrounding. All you need to do is start with sigma epsilon A T1 4 minus T surrounding 4, perform the factorization and separate out A delta T. So whatever is left is in fact HR.